Everyone, we're going to look at number 15 in section 4.2. We're going to find the minimum and maximum values of this function here. Again, your version of this problem might have slightly different values for the coefficients here, but should be very similar to this function. We're going to find the maximum values of this function on this interval. Again, this interval might be slightly different for your problem, but the technique will be the same. And the way we're going to find the max and min is by comparing values at the critical points and endpoints. So again, when we're finding the max and min of a continuous function on a closed interval, and this function is continuous certainly on the interval from 0 to 6. In fact, it's continuous for all real numbers. You might have concerns about the square root of something, but if you look what's under the square root, right, it will always be at least 1. Since I'm squaring the input x, I'm always going to have a radicand, the stuff I'm taking the square root of, that is greater than or equal to 1. So this is defined for all real numbers. It's continuous everywhere, actually. And so we are going to use decimal notation and give your answers to 3 decimal places. So make sure you're aware of that. On tests and things, I usually a lot of times will say give the exact value and then give a decimal approximation. So I'll talk a little bit about that, how you would do that on the test. So here is the function, and the first thing I would do before I do anything is to rewrite it, because we're gonna need to take the derivative, right, to find critical points. That's what we need. We have the endpoints, right? The endpoints are 0 and 6, so we need critical points. That's where the derivative is either 0 or undefined. So I'm going to rewrite this this way, right? The square root of x squared plus 1 is x squared plus 1 to the 1/2. And then when I take the derivative, 8's a constant multiple. And then what's left is a chain rule, right? I have the inner function x squared plus 1, outer function u to the 1/2. So the derivative of the outer function is 1/2 u to the negative 1/2, where the u is x squared plus 1, times du dx, the derivative of the inner function. And the derivative of x squared plus 1 is 2x. Don't forget minus 3x, right? What's the derivative of 3x? 3, so minus 3. Cleaning this up, I've got 8 times 1/2, that's 4. And then 4 times 2x is 8x. And the x squared plus 1 to the negative 1/2 is 1 over x squared plus 1 to the positive 1/2, or the square root of x squared plus 1 down here, right? So I can write all of this as this fraction. Of course, minus 3. So again, the derivative is defined for all values of x, right? Because same reason, the denominator here is never 0. It's always 1 or more, 1 or greater. And so I just want to know, when is the derivative equal to 0? Well, that's going to be true. Let me tell you, when this fraction here, 8x divided by the square root of x squared plus 1, is equal to 3, right? Because 3 minus 3 would be 0, right? So this will be the solution. How do I solve this equation? Well, this is a radical equation. First of all, let's clean this up by multiplying both sides by the square root of x squared plus 1. Let's get rid of the fraction over here. So 8x is 3 times the square root of x squared plus 1. And then how do we get rid of the square root here? Well, we're going to have to square both sides. So be real careful when I square both sides. Make sure you make use of the rule of exponents here. When I have a product raised to a power, right, I will distribute that power. And that's what I'm going to do here. 8x to the second power is 8 squared, which is 64x squared. And 3 times the square root of x squared plus 1 squared would be 3 squared, 9. And what is the square root of x squared plus 1 squared? Well, it's just x squared plus 1, right? The squaring cancels out, if you will, the square root. So here we are. We have no radical now. I do want to distribute this 9 through. And when I do so, right, it gives me 9x squared plus 9. Subtract 9x squared from both sides gives me 55x squared over here, equaling 9. Divide by 55, x squared is 9/55. And then I take the square root. Now, usually we'll take the plus or minus, right, square root. Notice I have only the positive one here. What happened to the negative root? Because that's also a critical number, a critical value, right, is negative 3 divided by square root of 55. Why is I'm not concerned with the negative one? Because remember, we're just looking on this interval only. You don't want to check any critical points or critical values outside this range. No critical numbers outside this range. So And this number here, by the way, is in that range, right? 3 divided by square root of 55 is about 0.4045. So it's between 0 and 6. Okay, so there's our critical point. This is what I mean by exact. And this is an approximation over here. And I'm typically going to ask on the test to give the exact value. You should also give an approximation because we're going to be comparing, well, actually, when we plug this into the function, the output will compare that to it. So just give the exact value. So here, what we want to do now is simply check the value of the function y. Remember, the function y was not the derivative, but the original function here, right? We want to check it at what? The critical points and the endpoints. I only have one critical point, so I list my endpoints. Remember, they were 0 and 6, and there's my critical point, 3 divided by the square root of 55. And then I just want to evaluate, right? If I plug in 0, it's pretty easy to see what I get. If I plug in 0, 0 squared is 0, plus 1 is 1, square root of 1 is 1. I just get 8 times 1. This is 8. 3 times 0 is 0. I get 8 minus 0. So notice I get 8. I can do that by myself, and then or without a calculator. And then what if I plug in 6? Well, it gets a little challenging now. 8 plus what? 6 squared is 36 plus 1. That's the square root of 37. And then 3 times 6 is 18. So I get 8 square root of 37 minus 18. So I can use the calculator to approximate it. This would be the exact value. This would be the approximation. And then what happens when I plug this in? Well, I'm not going to try and write that out. I'm going to actually use the calculator to help me get those values. So, and certainly as a check, you want to do this, right? And what you do is in the y equal, the equation editor, I'm going to enter this equation in, right? 8 square root of x squared plus 1 minus 3x. All right, and then I'm going to go to the table set and make sure I am in ask mode for my independent variable, so I can plug in my own values. And then I can plug in, 0, of course I get 8, 6, there's my, 30.662. And then this, how did I get that point? Notice it's not the rounded value here, 0.4045. What I actually do is type in 3, right? Notice it's down here, divided by the square root of 55, right? I'm actually going to type that in, right, into there. Now, when I hit enter, watch what happens. It gives you the decimal equivalent there of that. Notice you can highlight it. It's truncated because of the width of the column, but it's down here actually, right? That's the unrounded, at least as far as the calculator can do, answer. But again, here's the output over here, which is the 7.416. So notice here I'm rounding these to the third decimal place. Okay, so what's this mean? Now remember, if we have a continuous function on a closed interval, the extreme values, the maximum and minimums, right? Maximum, minima, will occur where? At either the endpoints or the critical points. So these are the only three possibilities. And so when I look at these three outputs, 8, 30.662, and 7.416, I just ask myself, which one's the minimum? Well, the smallest one, 7.416 is the minimum. What's the maximum? The largest one, which is what? 30.662. So that's the maximum. The maximum, notice, occurs at the right endpoint. The minimum occurs at the critical point. Okay, so that's the way we do these problems. Notice there's some of you might have already done the next section where we're talking about the first derivative test. There's no sign check done here. Sign checks are when we're looking at the sign of the derivative to help us determine where the function's increasing or decreasing. We don't do any of that here. We don't do a sign check of the derivative. We simply evaluate the function at the endpoints and at the critical points. Okay, I hope this helps with this one.